In this talk, I'm going to explain why we build React. And so first, React is a JavaScript library that we use at Facebook to build user interfaces. So in this talk, I'm going to first start to go way back in time and see a bit of the history behind it and why we actually built it. And then I'm going to see how we make it performant enough and all the cool optimization that we've done. So we're going to see also that computer science is not just like something you learn at school, but it's actually useful even for building web applications. So let's start by going way back in time, and in 2004, when Mark Zuckerberg was still in his dorm room. And the way you wrote PHP at the time is you were doing string concatenation in order to render your markup. And it turns out that this is a very, very good way to program, because it's really easy. You can hack something. You can be a backend engineer, front-end engineer, or even someone that doesn't know how to program, and you're going to get it working. And this is why PHP is so popular, and so many of the web is built on top of it. And so the website, the Facebook, the website grew a lot using string concatenation, and it was working really well. But at some point, there was one big issue with it, which is XSS injections. So if you write this code, it's not secure. So if an attacker is able to insert any string he wants, he's going to be able to run arbitrary JavaScript in your page. And the issue with this is this JavaScript is going to be executed on the users with the user's permission. So basically, you take over the entire user account if there's a vulnerability like this. And if you don't do anything, the developer is going to see it working, most of it properly, but it's going to be insecure. And the worst part is if you have one hole, like if you didn't escape one variable in your entire code base, you've got a vulnerability. So you're in a state where you have to have every single of your developer to care deeply about XSS in order to have a secure app. And unfortunately, it doesn't scale. So one of the things that you may want to do is to just escape every single variable in your entire application. But this doesn't work at all. Because if you escape something twice, then it's going to render some special controls, and it's not going to be a good user experience. And if you, by mistake, escape some markup, then it's going to show the markup to the user. So it was a point where it was really hard as a developer to build a secure product. And this is why in 2010 we open sourced XHP. So the way XHP is working is we extended the PHP syntax in order to put XML inside of it. And the great thing with it is now the XHP framework knows everything that's in the language, in the syntax, is markup. So you're not going to escape it. And everything else is content, and you're going to escape it by default. And so at this point, we had a way to build products as we wanted and get a very fast iteration cycle, but without being insecure. And so we started writing XHP only as a security fix. And it turns out that in XHP, you can also write custom tags. So for example, instead of having generic UL and LIs, you can have a talk list and a talk element. And we've built the entire Facebook website right now on the PHP side is using this. And it's very good because it lets you build using composable elements your entire website. So, and if you've heard about web component, about semantic web, and all of those, this is one way to do it, and we think this is the best way we know so far. So this was in 2010, and since then we've moved a lot of the application logic into JavaScript because we didn't want it to get the round trip, the client-server round trip time. And we tried a lot of JavaScript things. We tried a clone of jQuery, we tried data binding, but none of those solutions really were working well. And one engineer, Jordan Walk, told his manager, I'm going to port XHP to JavaScript. And he managed to convince him to give him 6 months in order to attempt this ReScript project. And so the first time I heard about it, I was like, there's no way this is going to work. But if it does, like, this is going to be huge. And 2 years in the making, I think like this bet was well worth it. So the first thing that everybody is, when talking about React, is wondering is, oh my God, I'm going to put XML into my JavaScript. And it turns out that we already had a lot of experience transforming JavaScript. So for example, at Facebook, we use all the new JavaScript extensions that are going to be in the next specifications. So for example, in this slide, I put the arrow function, but we also have classes, destructuring assignments, REST arguments, and many of them. And so we already had this like knowledge. And so it took like a week in order to write JSX. And this is not the main, like the main thing about React. So what was really difficult is the update model. So in PHP, it's really simple. If you go to another page, you're just going to re-render the entire page and send it to the client. And this is a very good model for writing application because you don't have to care about updates and mutation and, oh, this change, I also need to synchronize this change with this variable, etc., etc. And so now the big question was, can we make it fast enough if we use the same paradigm in JavaScript? And the answer is, not only is it fast enough, but it's often faster than the previous implementation that we had. And like, this blew our mind at the beginning, and it's still like really hard to convince other people that it's actually the case. And my talk is going to be about all the optimizations that we've done in order to make it possible. But before we talk about all these optimizations, one of my teachers said, you need to be right before being good. And what he meant by that is, you want to first have a solution, even if it's the most naive one that works, and then you want to iterate and improve the performance and improve the performance. Because if you try to make it fast from the beginning, then your project is very unlikely to succeed. So let's see, the most naive way to do it is we want to re-render everything on every update. So we are going to create an entire DOM tree of the new thing that you want to render, the new tree that you want to render, and you're going to remove the old one and replace it by it. And so this is probably going to be super slow and everything, but we wanted to know, at least, is it working? And it turns out that it mostly works, but it doesn't quite work for all use cases. And we've got like a lot of minor issues like input selection. Which input is currently focused? If you destroy the DOM and create a new one, you lose this input selection, input focus. And then you get text selection and scroll position. And you get all of those like small things. And the reason why is because the DOM is actually stateful. DOM nodes contain states like the currently selected input. So the first thing we tried was, well, I'm going to make a global variable that holds the currently selected focus. For each element, I'm going to store its scroll position and everything like this. And I'm going to restore it on the new element. So it worked for those. But for example, scroll position, if you're on a Mac and you scroll, you're going to see that there's some inertia going on. And there is absolutely no JavaScript API to control this inertia, to even read it or write to it. And so if we use this naive way, then you would lose scroll inertia. And for iframe, it's even worse. If the iframe content is located outside of your domain, then there's a security policy that says you cannot see and you cannot touch what's inside. So you cannot restore the state. So the DOM is not only stateful, but it contains hidden state from the programmer. So the way to fix this issue is we're going to try to reuse nodes. So instead of blowing up our div that scrolls, we're going to reuse it. So let's say in our first render, we render a scrollable div. And in our second render, we render another scrollable div. Then we're going to see that, oh, it's the same element. And so we're going to say, oh, this is the same, so I'm going to destroy the newly created one and just use the old one that's already in the DOM. So we're going to do that for all the tree, and it's working well. But at some point, in the new tree, you're going to have a new element. And so what do we do with this? Is we're going to move this element to the old tree, which is actually rendered on screen. And so with this, we're going to keep all the hidden state, but still be able to render new nodes. So this is a general idea behind how to make React actually work. And in order to implement it, we need to look at another concept. And so one guy called Adonis on Stack Exchange had a very interesting quote where he said that I tend to think of React as version control for the DOM. And what he meant by that is, before, in the old school way of doing programming, if you wanted someone to send something to your code to someone, you would create a zip file, send him. If you made a change, you would create another zip file and send him. And not only it was really wasteful, but it was really cumbersome. And what version control do is they take those two zip files and they compute a diff between the two. And the result of it is, oh, I'm going to delete those 5 lines and create those 3 lines and modify this word by this word. And what React does is really similar. We're going to take those 2 snapshots and we're going to output DOM mutations. Insert this element at this position, modify this element, remove this element, etc. And so at this point, we knew what we wanted, a diff algorithm for trees. So the logical thing to do at this point is we're going to look on the internet on all the academic paper and see what's the best algorithm for diffing trees. And it turns out that the complexity of it is O of n3. So let's say you have a 10,000 DOM elements in your application. So this is a big number, but this is not unthinkable of. And let's say you're able to do one operation in one CPU cycle. So this is never going to be the case, but let's imagine we can. And we have a CPU at 1 gigahertz. It would take 17 minutes in order to do the diff. So this is absolutely never going to work. And if you have ever done any computer science, like O of n3, it's not a good way to do things. But we need to start somewhere. We need to start with a naive implementation, and we want to optimize it for our use case. So how is the tree diff working? So the way it works is, for every new node in your tree, you're going to compare it against all the old nodes in the tree. And you're going to try to find the one that matches best. And for each of those pairs, you're going to match the entire subtree. So you get those 3 loops, and you get O of n3. But if you think about it, this means that you can move any DOM node from any place to any other place in the DOM with this algorithm. And in practice, in the web applications, you're probably never going to do that. The only use case I have in mind is drag and drop. But even then, this is not a common use case. So what we want instead is to only be able to move elements from children. So if you have a list of newsfeed stories, for example, you want to put a newsfeed stories at the top or in the middle, or those kind of operations are much more common. So we can actually simplify this algorithm, and instead of looking for any other elements in the tree, we're going to look only at the corresponding children. So we start at the root, and we look at the other root. Then we look at all the children from those 2 elements, and we diff them together. And then we do it for their children, and recursively again for their children. And so at this point, we now, instead of having a O of n3 algorithm, we have a lot of list comparison between all the children. So we reduced the complexity by a lot. And now again, if you look at the literature for diff algorithm between lists, you're going to look at the Levenstein diff algorithm. But we try to be a bit too good too fast, because Levenstein algorithm doesn't work in our use case. And in order to explain you why, I'm going to show you a little example. And this all has to do about identity. So let's say in the previous render you had 3 inputs, and in the next render you only have 2. So now let's put yourself in the shoes of React, and you see this. How do you match the 2 lists? So the most naive way you can do it is the first 2 are going to be the first 2, and then I'm going to remove the 3rd one. But the last 2 with the last 2 and remove the first one is also a valid solution. And it turns out that removing the first 3 and creating 2 new ones is also a valid solution. And so at this point, you're in React shoes. What do you do? And it turned out that all the solutions that I mentioned here are actually valid use cases. In some cases, you want one. In other cases, you want the other. So at this point, you're missing information. You only have the tag name. What if you could use something else? And something else is attributes of the DOM elements. So we started thinking about attributes, and one idea we had is we're going to make a hash of the entire tag name plus attributes and compare it together. But it doesn't quite work out. For example, value is a valid attribute. And now if you try to type OSCON in your input, then you're going to type O, S, and then if you do a hash between the two, they're going to be different. So you're going to remove the previous one and to create a new one. And so you're going to lose your cursor and the focus element and things like this. So it's not working. But we've got the idea. One attribute that's working very well is the ID attribute. So what's usually happening in practice for your forms is that you're going to put an ID which corresponds to the unique ID of the model that the input corresponds to. So for example, in this case, we have unique IDs that are of different lengths. And so at this point, React is able to do the link. It's going to link the ones that start with 9 with the one that starts with 9, and 5 with 5. And it's going to remove 42. And what's really interesting is it's another possibility that I didn't have in my previous examples. So this is working for this use case, but it's not working all the time. For example, if you use Ajax in order to submit your form, you're probably not going to put the IDs in the actual DOM. And now, if the IDs are not in the DOM, you're left with your previous issue. But the concept of ID is really important. And so we introduced a new special attribute with React, which is a key attribute. And the only use of the key attribute is to make this link between elements before and after in order to maintain the state of the DOM that's inside. And so at this point, we get it working. Yes. And it turns out that not only we get it working, but Levenstein diff algorithm was in O of n2 of all the lists. And now we can implement this using just a hash map and get it in O of m. So now all our operations on all the children are in O of m. And if you do the sum of everything, you get O of m. And so at this point, we are very good. Like, this is the optimal complexity that we can get in order to diff 2 trees. So we got it working. So now we got it working and we understand why the diff algorithm is going. And now we can start optimizing the hell out of it. So one of the main source of slowness from the DOM, from JavaScript application is a DOM. And Raphael on Stack Action as well has a very good illustration of it. If you look at all the attributes for an empty div, you're going to see a lot of them. And like it goes on and on and on. And the reason why is the DOM element is actually a very complex element. So it contains all the event interactions. It also contains styling, and it's positioned in the CSS selectors and all this caching. You also get a cache for all the unique IDs that links to DOM elements. And when you display an element on screen, it's actually backed by a buffer. So the DOM node also contains a buffer, maybe in the CPU or the GPU. And it contains a lot of things like this. But if you remember what we do with those DOM elements, their only use is to be part of the diff algorithm. And so we don't need like the buffer to be allocated or any of that crap. We just need to be able to compare two DOM elements in order to for the diff algorithm. And then the diff algorithm is going to output some set of mutations. So the idea is to introduce a virtual DOM. So instead of creating real DOM nodes, we're just going to create JavaScript objects that contain the tag name and the attributes. And then at the end, the diff algorithm is going to output a set of DOM mutations that we're going to apply on the real DOM. So this is the first big optimization that we've done in order to get a big speed up compared to our previous applications. So at this point, those are the two optimizations that we implemented when we open sourced. And so I want to take a little break and say how the open source project is going before going back to another set of optimizations. So it's going extremely well. So the trend is up to the sky. And if it continues like this, in 2 or 3 months, we're going to be the biggest Facebook open source project. So it's going extremely well. But those are all numbers, but actual real companies, even if we open sourced it 1 year ago, are using it. So for example, the New York Times is building a lot of interactive extensions for all their news coverage using React. So for example, if you look at World Cup games that were covered by New York Times, all the interactivity is done with React. GitHub yesterday just announced that they were switching their Atom editor to use React behind the scenes in order to render the editor. Khan Academy, since the beginning, was one of the first adopters, and now all of their interactive learning sessions and all of their dashboards are written in React. And probably the most intriguing and unexpected is Bearbank. This is the biggest bank in Russia, and they're converting all of their consumer-facing banking operations to React. So if you have some money in Russia, it turns out that probably it has to do something with React. And not only people are using React externally, but they're contributing back. And so 2 months ago was the first month where there were more commits from open source than from Facebook employees. So this really shows that we are trying to be a good open source citizens, and we get back a lot of value from open sourcing React. And not only that, but those commits are not just documentation typos or small feature, but actually big features came from open source. And I'm going to talk about 2 optimizations that were mainly driven by open source next. So if you have ever optimized JavaScript applications, you probably heard about reflows and repaints. And you're going to read about them in a negative way. So what is a repaint and a reflow? So whenever you do a modification to the DOM, if you insert an element or modify an attribute, then it's going to update the position of all the elements in the application, and you're going to want to change the actual pixels behind it. So it's a very necessary thing. Like if you do a change, you want them to appear on screen. But why it is a source of slowness in JavaScript application is because if you write normal JavaScript, you're going to do it more than once. And the pattern that's responsible for it is if you do a write to the DOM and then try to read from it, the browser is going to do all of those large operations for you to get a consistent view of the world. So the way you actually make it fast is you want to change your read, write, read, write, read, write patterns into read, 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 write, 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 read, 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 read. But it turns out that doing this, like doing all this synchronization, is really hard. And the same way our string concatenation example was insecure by default, if you write normal JavaScript, you're probably going to have reflows and repaint happening behind your back without you knowing. And so in order to fix this in React, this is where the batching strategy comes in. So let's say I click on a button, and I want this button to be modified somehow. The way you tell React to update is to call setState on this element. And instead of modifying this element directly in the DOM and doing the defilerism, we're just going to mark it as dirty for now. And maybe this is also going to update its parent. And maybe, because you're doing sloppy JavaScript or anything, you're going to call multiple times setState on the same element. But all of those states after the first one, it doesn't do anything. It just waits. This is already dirty. I'm not going to do anything. And maybe we're going to update this one as well. And so at this point, the event loop finished. And now we want to be able to flush all of this into the DOM in order to be displayed on screen. And so what's going to happen is we are going to start doing the actual rendering phase from top to bottom. So we only go through each element once. And now we start re-rendering the DOM. So by doing this, it's even better than read, 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 write, 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 read, read, read. Because if you think about it, this is only write, write, write. We never read from the DOM. We are in a write-only position with React. And if you also look about this, I said in the beginning that we're going to re-render the entire application on every update. And this is probably going to be slow. But now if you look at this diagram, I only re-rendered the subtree below any set state. So if you call set state on a small part of the applications, the rest of your application is not going to re-render. And if you start building React application, you're probably going to have small React components all over your place. And it's going to be fast because it's not going to re-render a lot of things. But the usual life cycle for your application is you're going to move the state up and up and up. And at some point, you may have your state at the root of your page. And at this point, re-rendering the entire thing is probably going to take a bit of time. And so to do this, we introduce the concept of pruning. And the idea of it is, if you just change something at some place, you're probably not going to want to re-render something that's completely different. And in order to tell React not to re-render some part of the tree, you can implement a function called shouldComponentUpdate. And this is going to have the next attributes and state of your component. and the previous one. And now you can do a diff between the two. And if nothing changed, you can say React, no, don't re-render this. So in this example, we're in our re-rendering phase, we're just going to ignore this entire part of the DOM. And so you can actually get like big speedups using this technique. And what's really important about this is you're going to add one line, maybe two, or maybe like refactor a bit, but you're not going to change your entire application in architecture in order to optimize it. And this is one very important characteristic of React. By default, it's fast, like fast enough. But then if you want to optimize it, you're just going to implement this particular component at some point, at some place, localized place in your application, and not have to like do a lot of things in order to get working. But if you do normal JavaScript, implementing this is very hard. And the reason why is, in JavaScript, you're going to have objects. And when you do a modification, you're going to modify these objects. And now if you try to implement shouldComponentUpdate, you're going to say, oh, what was a previous object? What's the next object? And it's going to be the same objects, but you actually modified it in between. And so you're going to say, oh, this is the same, this is the same. I'm going to return true, even if it's changed. So in order to implement it, David Nolan from the ClojureScript community had a very good idea of using immutable data structure. So the way they work is, whenever you do a modification, it's going to create an entire new structure. And now if you do the diff between the two, they're going to be different. So you can actually implement this optimization. And he built the OM library on top of React. And because in ClojureScript they use immutable data structure all over the place, he can implement shouldComponentUpdate by default on all the components. So maybe like in 10 years when everybody is familiar with the concept, we'll be able to do it by default in React, but we're not there yet. Instead, we have a more pragmatic approach, which is like, we're going to help you find the places where you should implement this that have the biggest impact. And the way it's working is you're going to run your application yourself and try to click on many things. And React is going to log every time you render a component, if it's changed or not. And if it didn't change, it's going to store the time it took to render. And so like 10 minutes after you played with it, you're going to call perf tool print wasted. And it's going to give you, oh, this component, if you implement shouldComponentUpdate, you can get 16 milliseconds or 1 second or whatever off of rendering time. So this is this component that you want to optimize. So we just released it last week, and we've been using it at Facebook internally like for a long time, and it's been really helpful to optimize React applications. So I'm done with optimization for today. And I hope that this presentation, you have a much better idea of like what the diff algorithm is and what's the virtual DOM and why we do batching and pruning and things like this. And I hope that you understand like the value of React in itself. So as for the project, we're now using it everywhere at Facebook. So for our desktop application, mobile application, for Instagram, and like basically all of the new products that we're starting are using React. So even if it's not 1.0 yet, like this is really solid, and we're using it to ship code to 1 billion users. And before we leave OSCON, I want to reflect a bit more about open sourcing React. So I started a talk with XHP. And at Facebook, we really love XHP, but we did a very poor job at open sourcing it. Like in 2010, we open sourced it, but no one knows about XHP. And if you look at the number of blog posts about XHP, before last year, there was only one on the entire internet. Even if we use it everywhere at Facebook, there was only one blog post. So we didn't go to conferences to explain why it's good, why it's bad. And like, if you're writing PHP code, I highly recommend you to use XHP. And with all the HHVM push, the PHP implementation that we have at Facebook, people are actually switching just to use XHP, which is really good. And it made open sourcing React harder, because not only we had to explain XHP and why you want to have XML inside of your JavaScript, but we also had to explain all of those crazy optimizations that we had to do to make it work in JavaScript. So it would have been much easier if people already knew about it. And for external community, they wouldn't have been shocked by, oh, this is completely new. Whereas at Facebook, we were like, oh, yeah, we went to XHP, and then this, and we had a continuum. So if I have one advice for you, is try to open source your project early, your important project early, because most of the time, your new projects are going to be based on top of them. So the more you wait, the harder it's going to be to open source and explain to people how to use it. So that's it for my React talk. I hope you enjoyed it.